Okay, let's begin with question number 4 on this paper. Let's move it to a whiteboard, please. Let's read and see. Okay, an ocean liner is traveling at 36 kilometers per hour on a bearing of 90 degrees. At 600 hours, the liner, which is 90 km from a lifeboat on a bearing of 315 degrees from the lifeboat, sends a message for assistance. So the lifeboat sets off immediately and travels in a straight line at constant speed, intercepting the liner at 0730 hours. So find the speed at which the lifeboat travels. Okay, let's try to see what's the meaning of the bearing first. So an ocean liner, okay, is traveling at 36 kilometers per hour, bearing of 90. So when we do bearings, we must understand the basic definition. That is, we measure it clockwise from the north. So when they say it's 90 degrees, that means it's like this way, and then this is 90 degrees. Basically, it's just a fancy way of saying it's traveling in a horizontal distance toward the right. Okay, horizontal right to be exact. Okay, so that we have the first diagram thingy. So it's going in this way, just a horizontal line. Okay, the ocean liner is going like that at 36 kilometers per hour. Just the ocean liner. I just put a dot here and I just mark that ocean liner. So this type of diagrams, they are sometimes, how do I say it? Two different things. One is the velocity diagram, and then the other one is the distance diagram. But both are kind of linked. So the velocity world, the laws of geometry must apply to that, and the, what do we say, distance world, likewise, the laws of geometry must apply to that. Okay, but we are using vectors, so that's why the velocity diagram is the main focus. Okay, now at this is 0600 hours. 0600 hours. So somewhere at 0730, a lifeboat came and saved them. Okay, let's try to see from the lifeboat's perspective. So I'm going to do a similar bearing kind of diagram sketch down here for the lifeboat. So for the lifeboat, if you read that, you see, they say it is 90 km away from this lifeboat and a bearing of 315. Okay, let's just focus of bearing of 315 from the lifeboat. So when they say it's bearing of 315 from the lifeboat, if I were to use that original diagram, because this is the ocean liner as a dot here, so the lifeboat will be somewhere here. So we just normally draw the north, south, east, west thing. So this is the lifeboat, kind of like the thing here. Please take note. So the 315 is speaking of, again from the north, all the way until here. This is 315 degrees. So if I were to modify the diagram so that it's a bit more easier to see down here, and that means the ocean liner is this dot and the lifeboat is this dot. And then I also can do a small modification, which could be important for this question. Which is the 315, if you subtract a 270, it's 45. Okay, the reason why I want to subtract a 270 is because up to here is 270. This line is 270. That means here is 45 degrees. And then because we can use the corresponding angles. So Z here, and this is 45 degrees. Okay, then you may be wondering what's the use of all this. Yes, this is the important part, because now I can draw the diagram correctly by indicating, let's say that the lifeboat down here. Okay, please take note, this is a lifeboat. And then this is 45 degrees. That's how we know this is 45 degrees without drawing too much, by doing the Z kind of actually, like this. This was the earlier 45. If I want to mark it here, and also I can remove it because it's not necessary for a triangle at this point. To keep the diagram as simple as possible, only with the most important information. Okay, 90 km is a distance. So that's why I have to write here 90 km like that, between the ocean liner and the lifeboat when they send a message for assistance. Okay, now the mayday like that. So the ocean liner from here, just imagine the triangle moved, and then from here, it's when the whole drama starts. So it is starting to run like that, going on like this. The lifeboat sets off immediately, no time lost, travels in a straight line at constant speed, intercepting the liner. So this is the point of interception. Okay, point of interception, but I just put intersection, same thing, huh? Mathematically same. Okay, okay, that means, so it's in the constant speed. And we need to think about now at 0730 hours. So now it makes sense why I marked it there. Okay, so now this is partially a diagram because we want to link to a velocity diagram, the vectors of velocities. Okay, so I just draw back here the velocity diagram, maybe down here, let's beside it. Down here purely to be a velocity diagram. Okay, let's mark these things more accurately, please. Velocity diagram purely, because there's a mixture of some numbers there which we don't want. So this is like 36 km per hour. So you can already see that this is a velocity v in which we need to find. So this is one, actually velocity, we can find the direction as well. As you can see here, we can find this one, but they're only asking the speed. So basically speed means based on the velocity. So I put a vector symbol. Speed is just the modulus of the vector. Oh, so now we understand. So that is why I can just call this as v, the modulus of it. Okay, so to transfer here, we need one more info. Notice something seems like not enough, which is true, which is that from 0600, okay, let me just show it like this. So 0600 to 0730 hours, it is 1.5 hours, 1 hours and 30 minutes. Why am I calculating in hours? Because of the unit, the unit sensitive km per hour given in hours. So we must make the unit to be same. It's a unit trick, sometimes we used to use that phrase to give an alert of that. So here we have 90 km only. So what is this line? So this line itself, it's not something, this is why maths and physics comes, that means they kind of like link together, which is a concept of abstraction. Abstraction means sometimes we label a diagram something that didn't happen in reality. So in this instance, that will be represented by this 90 km per hour. Imagine the ocean liner did not move. So if the ocean liner did not move, then we're talking about a relative velocity. And then within the same time, so time is the invariant, okay, that doesn't change. Within the same time of 1.5 hours and this 90 kilometers per hour, if you'd have traveled like that, the lifeboat, towards that ocean liner, then that is the relative velocity because all are happening in the same time. That links the whole diagram, keeps it fixed. Aha, now you know the trick already. So the relative velocity idea helps us to link it like that, and we can get the velocity if it happened like that. The abstraction part, if. So abstraction is based on an if. It's not the actual thing that occurs here. So let's try to calculate this relative velocity. It's just still distance over time, except that the distance and time are, the distance is 90 km away because the lifeboat and ocean liner were 90 km away. And in just 1.5 hours of traveling, that means it would have reached in 1.5 hours means it is the same as it's going at 60, when you divide this, 60 kilometers per hour in the right unit. Oh, so this is the crux move. This is the hard part. But when you can understand this part, that means in the velocity diagram, I would mark it as 60 km per hour. And then the upper part, now I show the unit, is km per hour. So it's a purely a velocity diagram, no distance and all that. So when all three things are velocity, now I can link them using geometry. So the laws of geometry must be obeyed. So this is the part where it becomes a bit like geometry. So the geometry part, and then please take note, this 45 degrees still is maintained. The 45 just now we got for the bearing. So bearing argument is just to give that angle there. Now it's quite obvious that we must use the cosine rule. Okay, let's use the cosine rule and solve it plus. So cosine rule tells me that v square, or this modulus of v, you'll know already, right? This one is then 36 square plus 60 square minus 2 times 36 and 16 cos 45. Aha, the opposite one. Okay, please take note. This one just put in the calculator. Let's compute it plus. So this is, the calculator straight away, 36 square plus 60 square minus 2 times 36 times 60 times cos of 45. So it seems to be v square is like 1841.298705. I just like to copy everything in the calculator so that the next line I can give a more accurate answer. Please take note, when you square root it, it becomes 42.9 kilometers per hour. Good to maintain it as that, 3 significant figures. Okay, so that's the thing. One last comment. If for some of you, we may have forgotten the cosine rule. Remember not, cosine rule means, cosine rule should be something like this. Let's say label this nicely, just write the rule here. So in this instance, let's say it's A, B, C. So C is what we're going to find, small letter C, small letter A, small letter B. Let's say I write it with respect to C, in that order, like that. C square will be A square plus B square minus 2AB cos C. So it doesn't matter. Even if it was B square, we needed to find the other two letters, A square, C square minus 2AC, cos of the opposite capital B. So with the correct labels, it becomes easy to remember like a pattern. So A square means B square plus C square minus 2BC, cos of capital A. Aha, so this is the cosine rule that we are using to solve the problem. Huh? All right, that's it. Thank you.